For the mass of Jupiter, first you have to understand Kepler's laws of planetary motion. The first law is that every planet's orbit is an ellipse with the sun at its focus. The second law is a line joining the sun and a planet sweeps out equal areas in equal times. The third is that the square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit. First, we start out with the equation F equals ma when we're trying to derive this formula. We then can use the orbital gravitational formula and plug that in for F right here. We also know the centrifugal acceleration formula is v squared over r. Our next step is to cross out the masses because there's the two masses on both sides. This gets us down to g times the mass of Jupiter over r equals v squared. With the v, we know that we're doing distance divided by time equals velocity. The distance in this case is going to be our period, which is 2r or 2 pi r divided by our time. This we can then plug in for v to get 2 pi r divided by t squared. From here, we give out the squared to every number in the parentheses, making it 4 pi r squared divided by t squared. We then multiply by r on both sides to get rid of it underneath the g equals g times the mass of Jupiter. This simplifies all the way down to g times the mass of Jupiter equals 4 pi r cubed times t squared. From there, you just divide the universal gravity constant to get the mass of Jupiter equals 4 pi r cubed divided by g times t squared. To find the periods, we can use the chart and find just the times at which the period will repeat itself. So for example, with Io, we found that at 1.3 and 3.2, the period would repeat itself. I was able to calculate that by subtracting 1.8 from 3.2 to get 1.4. This is the period that I will use as my days. I then needed to convert my days down to seconds. To do that, I know that 24 hours is in 1 day, 60 minutes is in 1 hour, and 60 seconds is in 1 minute. You then can multiply the top numbers to get our final, that 1.4 days equals 120,960 seconds. We also needed to convert kilometers into meters. This number we got from the radius or the orbit that the moon makes with the Jupiter. So this number, for example, was 421,600 kilometers. We then multiplied it by 1,000 to get our final number. To do the math, we now just plug all these numbers into the formula that we had. For example, we take the kilometers that we converted into meters and plug that in for our r. Then we do the same with the t using the numbers that we got from the days converted down to seconds. We know this number is the universal gravitational constant, the 6.67 times 10 to the negative 11th. I multiplied the top all together and multiplied the bottom down together to get this number, and then was able to simplify it all the way down to this. For the next planets, we're just going to be doing the same thing, where we take our period that we got from the chart and multiplying it by 24 hours, 60 minutes, and 60 seconds to get our final days in seconds. The same thing that we do for kilometers, where we take the large number and multiply it by 1,000 to get our final in terms of meters. We're going to use the same process of plugging in the numbers that we just got, with the radius being the days converted into seconds, the kilometers converted into meters, and the time converted from days to seconds. We multiply the top and multiply the bottom and simplify it down. We're using the same process, this time just with a different amount of orbits. So this would be 7 days converted down to here times the seconds. This is now the kilometers converted to meters to get this number. We use the same process of plugging in the numbers, this being the kilometers to meters, and this number being the days in terms of seconds. and our universal gravitational constant, multiply the top, multiply the bottom, and you can simplify it down. This, for our final one, we just repeated the same process. This time it was 17.9 days and converted down to 1,005,406,000 to 560. We then took the kilometers and converted it to meters to get that final answer. We just plugged in the numbers, repeating the same process, multiplying the top and multiplying the bottom to get this final number. In the end, we were able to plug it into our graph by making the x-axis, or the y-axis, equal to 4 pi r cubed, and the x-axis equal to g times t squared. This allowed us to get kind of a straight line, even though it's not perfect, just because of different reasons of error. To finally calculate the mass of Jupiter, you can use the slope. I used Io's and Europa's, so I took the y2 minus y1, x2 minus x1, and was able to simplify it down to get my expected mass of Jupiter. The real mass of Jupiter is actually 1.898 times 10 to the 27th, whereas I got 1.53 times 10 to the 27th. My percent error was 19.15%. Different reasons this could have happened was because of the periods weren't exactly precise. And I believe it doesn't make a difference if the radius or the periods were different. I think using this example, if the real answer was 200 divided by 400, it would be equal to 0.5. If you were to change the radius and make that 10% off, it would be 20 divided by 400, which would be 0.05. If you were going to change the other number in the opposite way and make that 10% off, it would be 200 divided by 40, which equals 5. In all of these scenarios, they're the same amount different from this, just 10 times less and then 10 times more. To determine the period, you see how long it takes for the object to return to the same place it started. You can track how long the moon would take to get to its original spot. And then this method that we use to find the mass of Jupiter can be applied to find the mass of any orbiting object. The equation m equals 4 pi r cubed divided by g times t squared can be used for any two orbiting objects around a mass. You can find the slope of the objects to calculate the mass when you use it in a graph. And that's it.